So now let's consider about Hadwiger number. So one of the important problem, in graph theory is, one of the well-known problem is this four-color theorem. Four-color theorem says that any planar graph can be colored with four colors, and it's proven by the computer, proven with the computer assist. And there was that Hadwiger conjecture, which, is stronger than four-color theorem, says that if G has no KT minor, let's say KT plus 1 minor, then it is T colorable. And in other, it's you can rephrase it that if you are not T colorable, then G has a KT plus 1 minor. So this is more general than four-color theorem, because four-color theorem says that if you have a planar graph which has no K5 minor, so it should be four-colorable. And so here we are interested, what we are interested in is this complete graph minor in G and chromatic number. It suggests the relationship between these two. So this essentially says that instead of considering the chromatic number, one might instead consider the largest complete graph minor in G. So that motivates to define this number. Let's say the Hadwiger number H of G of a graph G is the maximum M such that G has a Km minor. So with this definition, we can simply write that this Hadwiger number is at least the chromatic number for all graph G. So we want to prove this. But of course this is open. So let's write this conjecture is that this is at least, say, K, for K is the chromatic number of G. So it's known for K equals 3 and 4 are not too difficult, and 5 is equivalent to four-color theorem, and 6 is known to be true, and they use the four-color theorem to prove the case when this is 6. So as this is a difficult conjecture, what people do is instead of proving this inequality, they might first try to prove a weaker inequality and keep strengthening it. So current, best bound is recently Norin, Song, Hossel proved that this Hadwiger number is at least some constant times K over log K to 1/4 plus some small number. So this is the best known lower bound of this Hadwiger number. So what they did is they build on the previous results by Kostochka and Thomason on a weaker lower bound, and they strengthen it. So what we will prove today is the Kostochka and Thomason's weak bound, which is weaker than this. So one of the way of attacking this is that here, so we want to, when this Hadwiger number is fixed, we want to upper bound the chromatic number somehow. And there are several ways to upper bound the chromatic number. One of them is using the degeneracy. We know that the chromatic number is at most, say, r plus 1 when r is the degeneracy. Let's say degeneracy. So if we can somehow bound the degeneracy in terms of Hadwiger number, then that will lead us to some inequality where this Hadwiger number is on the right hand side, and left hand side you have some expression consists of this chromatic number. So which maybe, which motivates to study the relationship between degeneracy and this Hadwiger number. So that's exactly what Kostochka and Thomason did. So again, this degeneracy, can be expressed as the number of edges in a given graph. So when we have n vertex and then we know that the number of edges is Rn, then there must be a vertex with degree R. Let's say, okay, if it has an average degree R in here, and then every subgraph of it has an average degree R, then it has degeneracy at most R. If it has average degree R and it doesn't have a it has a high degeneracy, then we can instead taking a smaller graph with a higher average degree. So average degree in this subgraph is kind of same with degeneracy. Anyway, so if in sum, so instead of studying the relationship between Hadwiger number and chromatic number directly, one can first try to establish the relationship between Hadwiger number and the number of edges, say average degree. And from average degree to chromatic number, we know some bounds, which comes from the relationship between average degree and degeneracy. So anyway, this motivates to study the relation, which is this result, which was proven by Kostochka and Thomason independently. So they show that there exists a constant C such that every graph with average degree at least C times T times square root of log T has a KT minor. Give me a moment. So So if we have this, then what it means is that if this Hadwiger number is, say, t minus 1, then it has no kt minor. Then average degree is at most c times t times square root of log t on G. But this not only holds for on G. If you take a subgraph G prime of G, this again doesn't have a large kt minor. So we know that Hadwiger number of this G prime is again at most t minus 1. So again this has average degree at most this, meaning that this G is this degenerate. So we know that its chromatic number is also bounded by this. So this shows that when this chromatic number k is given, then the Hadwiger number t, up to minus 1, is essentially some constant times square root of k over square root of k. So this gives a bound which is a bit weaker than this current best known bound. So this actually implies this relationship between Hadwiger number and chromatic number. So we will prove this. Yeah, by the way, I forgot to mention that in the previous video, I said that the K color graphs forms a minor closed family, which was not true. So yeah, sorry for the mistake that I said. So anyway, so we want to prove this Kostochka-Thomason bound. If we have a graph with many edges, average degree at least this much has a kt minor. So what we want to do is we have this graph G with that many edges. Then we want to build kt minor. So what we want to do is we want to first take a minor of this, say H, so that the H is, it's dense. Meaning that when, say, this number is given, let's say this number is like 100, G could be huge. G could be huge and each vertex has degree roughly 100 or plus minus some, roughly close to 100. Then what do you want to do is you first take some connected subgraph and then you contract so that in H here, so this degree 100 is much smaller than the number of vertices in N. But after contracting it, this H has much smaller number of vertices, while its degree is still roughly 100. So that this 100 is actually bigger than, say, N has M prime, H has M prime vertices, then it's bigger than some number proportional to M prime. So later we will show that this is actually possible. So this is the first thing that we want to do. And now we have this H. And all the vertices has high minimum degree. So that with this condition, we, for example, know that every two vertex has a common neighbor. So which is good for us. Now what we want to do is here, if we have this graph, let's again call this H. What we do is we take some vertices x1, which forms a connected graph. and then we take out. So here we have x1. So x1 is connected. And moreover, this dominates many vertices here. What I mean by dominate is when we have x and then here we have y. If y have a neighbor here, then we say that this y is dominated by x. And another vertex, it has some neighbor, then this g is dominated by x. But if there is some vertex x which doesn't have any neighbor in x, then this is not dominated. So x1 dominates lots of vertices here. And then what do you do is we want to take x2 here, which has an edge to x1 and which forms a connected subgraph here. And then we again take out x2. There is edge between and each of them is connected. And again, this dominates a lot of vertices. We can take out this x2 because x1 is already dominating lots of vertices. And again, now we want to take x3, which is connected, and then which has edge to x1 and x2. These edges can be found because x1 and x2 are dominating lots of vertices here. And we again take this x3 out, and which dominates a lot. We want to keep repeat. So that's vaguely how we want to do. So for that, we need to collect some lemmas first. So in the next video, we will collect the lemmas.